I've been working with Apple in FoundationDB for around 4 years. So I spent a significant time in integrating RocksDB as a supported storage engine in FoundationDB. So I'll discuss that journey in the today's talk. So this is the agenda for our today's discussion. So we'll start with the motivation behind this change, and then I'll cover the RocksDB fundamentals before diving into the FDB-specific RocksDB implementation. And then I'll talk about what testing we have done and what challenges we ran into. And finally, we'll discuss the storage engine migration process. This is helpful if you have a foundation cluster running, and if you want to change the storage engine, the process would help you to understand. So why did we decide to add a new storage engine? The main driving factor for is storage space efficiency. So we were looking for better physical footprint for our logical bytes, which means that we are trying to save some space and accommodate more logical bytes with the same set of physical bytes. So one way to achieve was to use compression. So RocksDB helped us, RocksDB compression facility helped us in achieving that. And coming to faster garbage collection, it was not our initial motivation, but it got as a byproduct of using RocksDB. So we had issues sometimes with available space going down below our thresholds when, even though the data is balanced across all the storage servers, even though we have free space in the system, because the deletes are marked for deletion but are not available yet for reuse. So with the RocksDB compaction process, this helped us to get the get the deleted space for reuse much sooner. So for the next set of features, we are looking to support file-based operations on the storage engine through checkpoint and restore. So this is to enhance the data movement and backup restore features. Currently, our data movement and backup restore features share the same write queues and read queues with the user traffic. So we are anticipating with the file-based features, we can eliminate some of the contention and can also do it them much faster. So this is a high-level overview of FoundationDB. I'll not go into detail into this, but if you see the architecture diagram on the right side, the main topic for us is our storage servers and storage engines. I just want to mention that this is the part of the storage system that you see in the architecture diagram, which is part of the data plane. And the storage systems mainly tries to interact with the log systems and the clients to serve its purpose. So let's see what are the responsibilities of storage servers and storage engines. So basically, storage servers are processes which are mainly responsible for managing a set of assigned continuous key ranges, which are nothing but called as shards. And it tries to handle multiple of them. And it also ensures that the commits that are happening on the cluster are persisted onto the disk by. So basically, it helps you to apply the commits from log servers asynchronously and persist them onto the storage on the disk. So, and it manages all the key value operations with the help of storage engine. And coming to the storage engine, it's embedded in the storage server. It basically handles the actual data storage and retrieval part. It implements an on-disk data structure to do the storage and the retrieval part, which can be like an B tree or an LSM tree. And it supports all the key value operations like inserts, updates, deletes, and reads. So FoundationDB have several storage engines supported, including SQLite, Redwood, Memory. From 7.3 version, we would be supporting RocksDB as well. Let's talk about RocksDB. So it's an embeddable persistent key value store. Because of its embeddable nature, it's a perfect candidate for to integrate into the systems like FoundationDB. It's an open source, which is similar to FoundationDB. and it manages its data on disk in a log-structured merge-tree data structure. And it has inbuilt support for compression and checkpoint and restore, which FTB wants to leverage. And it has a big and active community and used in several large-scale systems. So here is a high-level overview of the RocksDB. So coming to the write path, if you get a write onto RocksDB, it writes into an in-memory active memtable structure and also writes into an write-ahead log, which is persisted on disk. Once this is done, it ensures the durability of that particular write, so it returns back to the caller. And there's several background tasks that runs after this. The writes keep writing into the active memtable, and once the active memtable is full, it moves into a set of immutable memtables, which are still on memory. And there is a background process called as flush, which actually takes this immutable memtables from memory and flush them to the disk as SSD files. These SSD files are nothing but continuous key ranges, and these are organized into multiple levels ranging from L0 to Ln. And these are all immutable. And we have another background task called as compaction, which helps in flushing these SSD files from upper levels to the lower levels. This is to ensure this is to help to reduce the read amplification and also reclaim the deleted space faster. Similar to the write path, the read path also takes the same flow. Basically, if you get a read onto the RocksDB, it looks for that particular key in active memtable, then to the immutable memtables, then onto the SSD files from level L0 to Ln until that particular key is found. So coming to the FTB RocksDB storage engine, it also implements the same key value operations that all other storage engines have, like basically reads, writes, deletes. It is also slightly different in the way it is implemented. We implemented it as multi-threaded. So by default, it comes with one write thread and 4 read threads and several background threads to do flush and compaction. RocksDB has tons of options. It's highly tunable. So we try to provide some of these options as FTB knobs so that FTB users using RocksDB storage engine can tune the RocksDB storage engine based on their workload and the hardware resources available to them. So some of the options include compression settings, memory settings, compaction policies, throttlings based on compaction rates, and some I/O behaviors like Bloom filters, prefix filters, and block cache. And also slightly different with respect to the logging part or the observability part. So we specifically have RocksDB metrics, which focus on the internal metadata of the RocksDB storage engine. So these help us to understand the performance and also helps in debugging issues. So we have these metrics available in status.json, which is a client API to collect the metrics. And we also have trace events with type equal to RocksDB metrics. And apart from that, we also have several log files specifically containing the detailed RocksDB information in the same directory as FTB trace files. And these are auto-cleaned up after 15 days. So here is a quick side-by-side comparison check between the first initial storage engine SQLite and the RocksDB storage engine. So SQLite uses B-tree and does in-place updates, where RocksDB uses log-structured merge tree and mostly try to merge the SSD files instead of doing the in-place updates. And SQLite doesn't have any compression support, where RocksDB does have. And to achieve concurrency, we use flow actors in SQLite, whereas in RocksDB, we use flow actors and threads. And to reclaim the deleted data back to reusable state, we use a process called as vacuuming in SQLite, whereas it is done through compaction. And SQLite in FDB doesn't support any checkpointing and restore, whereas RocksDB has this in inbuilt. And how did we test it? So apart from the regular key value store unit tests, we have simulation coverage too, where for every simulation run, we randomly pick a storage engine and test it. So it covers the testing for all storage engine types. And apart from this, we also used an interesting feature called as testing storage server. So this helps you to test your storage engine in production clusters in real workloads. So basically, it creates a shadow copy of the real storage server. Both start as empty. They get same set of reads and same set of writes. And at the FTP client level, when it gets a read request, it sends the request to both the shadow copy and the real copy and collects the response and compares them. If there is any inconsistency in the response, it reports. So this helps in ensuring the correctness of the new storage engine. And only the response from the real copy is returned to the clients. And the FTP client also has a histogram to compare the read latencies from both the storage servers. So this helps in comparing the performance too of both of them. Apart from that, we have storage level metrics, which can be used on both a real storage server and shadow copy to compare the performance. Like probably you can also compare the latencies, and with the process metrics, you can compare the resource usage like the disk and the CPU. So this helped us a lot in testing our the new storage engine in our production clusters with the real workload. Yeah, RocksDB has its own challenges. So one of the great feature of FoundationDB is deterministic simulation. This helps the FoundationDB to ensure reliability always. So, so we wanted to continue this even with the RocksDB. So RocksDB made that part a little difficult because we had RocksDB we had some simulation decisions which are made on RocksDB metadata. Since RocksDB is not deterministic, the decisions in simulation in storage server were also not deterministic. So we lost the deterministic there. So we had to put some extra efforts to write some workarounds to ensure the determinism is working. And because of compaction and constant push of SSD files from upper levels to lower levels, there's like little higher resource usage compared to the other storage engines with respect to CPU and disk. And RocksDB in general is very sensitive to delete operations. If you have a burst or very focused set of delete operations in a particular key range, we see the spikes in read latencies. And since RocksDB is having a big active community, if you're planning to upgrade or downgrade RocksDB releases, we need planning and efforts and testing efforts, additional efforts to do that. So the migration process. So if you have a cluster which is running with any storage engine, and if you want to move to a new storage engine, we can use a process called as perpetual storage wiggling. So here I take an example where you want to change the storage engine from SQLite to RocksDB, but it can be anything. So basically it picks a SQLite storage server, it excludes it, which means that it removes that process from the cluster. So as part of that, it moves data from this excluded process to the other storage servers. And it includes back the storage server. When it is including back, it ensures that it's picking up the new storage engine. In our case, it could be RocksDB. So as the process gets added, the DD kicks in, the data distributor kicks in and tries to balance the data. So it tries to move the data back to this storage server, and it starts working with the new storage engine. So it repeats the above two steps for all the storage servers. It's an in-place conversion, so it doesn't require any additional hardware. It's an automated process, doesn't require any manual intervention. And it also, the speed of the migration can also be adjusted to do multiple migrations at a time, or whatever number you decide. It has its own feature of pausing and resuming itself for external issues. Suppose the cluster is not doing good or overloaded or working on its fault tolerance, it will pause itself and resumes back when the cluster is back to normal state. Yeah, so what are the next steps after this? Yeah, we want to leverage the file-based support with checkpoint and restore for different use cases like data movement and backup and restore, which RocksDB is providing. So that's the next steps. Oh, yeah, that's the end of the slides. Any questions?
Hello. So first of all, this was amazing to hear about RocksDB. I just had one question. It's great that we're doing checkpointing as well, but I had a question there. As per my knowledge, checkpoint increases the latency because you store the values that you've already calculated. So how frequent is the checkpointing done, and uh, is the latency dependent on that? Is it some kind of uh, limitation as well?
And like we haven't started using in data movement and backup and restore, but yeah, it should be. I think there's a possibility of increasing the read latency. That's what the RocksDB documentation tells. Um, but we are hoping it would be better using than the front-end pipelines than to use the physical file-based systems. So physical movement of files around. So yeah, we have to experiment on how frequent of checkpointing would affect that. So yeah.
I just had this question. So.
Great talk. I just had an open-ended question slightly, which is if there was something that you wanted from RocksDB that you couldn't get, what would that be? And if it's single-threaded determinism, do you think that that is a feasible thing for RocksDB to implement? And do you feel like it's something you would value a lot?
Oh, so coming to your first question, you said what we are not getting from RocksDB. Okay, that's an interesting one. So
I remember you said that for simulation stuff that it was non-deterministic, and so that was a problem. So I presume one of the things you would want is a single-threaded version of RocksDB so that there is no lack of determinism and there you can run all kinds of simulation stuff. Is that one of the things?
yeah, but we also want to test the thread model in the simulation. So even though you start running with single thread, that might not simulate what you see in the production cluster. So it
Exactly.
might not help. So wherever we wanted to take simulation decisions based on RocksDB metadata, we try to ensure that we are trying to take randomly deterministic decisions rather than any value. So in the FTB, we have a seed value, and every time when we want to diverge the code path, we ensure that it's following the same seeds. So we try to ensure that it's getting followed all across by taking by doing some of these workarounds.
I see. Thank you.
So what are the consistency guarantees of this kind of setup with FDB plus RocksDB? For example, for a write to get propagated to the lowest layer, it might take a while, right? So what values read during that interim?
Oh, so we use MVCC. So basically, our storage servers maintain the writes for all the recent writes in the last 5 seconds. So when you get a read, you get a read version, and you can read only for a version which is in that time range of 5 seconds. If you're reading anything before that, we would be rejecting that read. So, and storage service ensures that they maintain all the writes that happened in the last 5 seconds and returns those values for all the reads.
Okay, thank you.
I have a question. So does this mean we can get, push button snapshot and restore?
I'm sorry, can you repeat?
Like today when we do backup and restore, um, right? It's a fairly involved, expensive process, especially restores of multiple terabytes of data, especially if you're deployed on public clouds. So with this feature, is it possible to have a much faster restore?
Yes, we are hoping for that because we can use movement of files. So we can upload to backup, S3 backup or any iCloud backup. The checkpoint and restore files is physical data movement, and when we're restoring back, we can restore them back the same as files. So it doesn't have to go through the front end transaction layer to the entire transaction layer and the transaction log servers. So it can directly go to the storage server. So it should eliminate all of that code path. So it should be faster is what we're hoping for.
Okay. And then you mentioned there are challenges when you do deletes. Could you maybe expand on, what are the real world implications of going with RocksDB? And if you have workloads that have a lot of deletes, and is it point deletes or range deletes?
Both of them can cause the increase in the read latency. So for a use case, suppose of a queue-like data structure where you get constant inserts and deletes happening, and if it is like a particularly in a specified key range, then there would be a more focused set of deletes happening there. So it takes time for the SSD files to get compacted down to the lower levels. Until that point, we would be seeing the read latency spikes. So if it is constant and if it is continuously happening like in a queue-like data structure, we could assume that the read latencies would be higher for such cases.
And one last question. With respect to the write amplification on the storage, is there a comparative number, Redwood tree versus RocksDB, in terms of how much more better is RocksDB for the amplification story?
I don't have any Redwood comparisons, but with SQLite, I observed the depending on the workload, but at least I observed 5 to 10x more write amplification than SQLite.
Sorry, my question is more if I'm writing a gigabyte of data, right, with a replication of 3, it actually turns out to be using 5 gigabytes in terms of storage because of the B tree amplification for the Redwood. Is there such an amplification in the RocksDB storage engine, or there is no amplification whatsoever?
So you're saying for writes? Is it for writes? Or?
But from the storage perspective, right? Like if I want to store a terabyte of data, with replication factor 3, I would assume that I need 3 terabytes of disk, but in reality, I need 5 to 6 terabytes of disk with at least the Redwood engine because of the internal B tree amplification that happens, right? So I'm curious, in RocksDB, if I were to move, does that picture change?
I'm like, I don't, so we're talking about the space amplification here.
Yes.
Okay,
yes.
so I didn't see any amplification with respect to space. It might take some for metadata, but we have better results compared to SQLite.
Was there any comparison done with respect to performance, reads and writes for similar workloads between RocksDB and SQLite?
I'm like, so we tuned the RocksDB storage engine so that we have similar performance as SQLite, but still gaining some disk space savings. So we are doing good there with our workload and hardware resources available to them. But I think it can keep changing depending on what workload you're running and hardware resources.
Call. Check. Last call for questions before we move with the next presentation. Any other questions for Neethu? Okay, if there's no more questions, Neethu, thank you so much for this presentation.